all have seen this diagram but did not note a fundamental contradiction. That's a foundation of optics, but if it were 100% accurate, your magnifying glass would create a point of infinite energy. Literally a black hole, and I can prove it using nothing but elementary school math. What exactly happens at this point? The intuitive answer, it's the place where all the light is concentrated. But if we take this picture too literally, something strange happens. Let's look at the mass. You will see where exactly it breaks. If we take a fixed amount of power and divide it by the area it covers, we will get intensity. Simple, right? But there is a catch. Now imagine how the lens concentrates the light into a single mathematical point. At this point, the area shrinks to 0. And if S goes to 0, intensity goes to infinity. In other words, this diagram predicts infinite brightness. In physics, if we see infinity, it's a warning sign. That means we are missing something fundamental. Yet no lens has made infinite brightness. Math says infinity, and everyone has seen a lens, and no lens did it. The reason is not just a flaw in the glass. The reason is physics itself. Something is really fundamental is missing in this picture. But the real question is what exactly happens at the focal point. The answer forces us to stop treating light as simple rays. Every framework has certain limitations, and we clearly reached it. We run into a surprisingly awkward problem. If the focus is not a point, then how big is it? That sounds like an easy question, and for solid objects it usually is. The diameter is whatever caliper it's simple. But not each object has well-defined boundaries. For instance, cucumber. What's the diameter of cucumber? 4 centimeters? 3 centimeters? It depends on whether you measure it and how fresh the cucumber is. The light beam is even worse. It has no hard edge at all. There is no place where a beam suddenly ends and darkness begins. The intensity just fades away gradually. So when we say this spot is smaller than this one, what exactly do we mean? How can we measure it? There is no lens which can make infinitely small point. It's always a spot. The obvious explanation, probably our lenses are not that good. From the very beginnings of telescopes and microscopes there was a simple expectation. The better lens should produce the better image. Probably the lens wasn't shaped as intended, or there is a problem with glass quality. And for a while it looked obvious. Make glass purity better, refine polishing, and the focal point should theoretically get smaller and smaller. But something strange happened then. Even as manufacturing dramatically improved, the focal point refused to collapse to a mathematical point. The images we saw through a microscope got sharper and sharper, but when we focused a light into a spot, it remained a spot. Nowadays we could use the purest glass ever synthesized. We can polish a lens with an atomic precision, and still we are hitting that limit. And it's not just an academic puzzle. The smaller focus we can get, the sharper image we are getting through a microscope. The smaller feature we can manufacture and manipulate. Microscopes, semiconductor industry, laser machining. All that needs the smallest possible focus. Every nanometer we shave off that spot is not just a win, it's a huge jump for our civilization. And it forces us to confront two fundamental questions. Is that blur it's a problem of engineering, or it's a law of nature? If a perfect point is impossible, what then replaces it? Please don't forget to like the video, it's really important for my growing channel. Earlier we ran into a surprisingly awkward problem. A beam of light doesn't have a well-defined border. It's not like a solid object which has a certain moment where it stops to be. Beam of light just fades. It means any definition of its size is to some extent just a convention. If you take light from a common lamp or a sophisticated titan sapphire laser, you will see that the beam has often complex, to put it bluntly, ugly shape. It's a chaotic landscape of intensity. So how do we assign a certain number to this mess? How do we say which size does it have? One way is to write a circle, which encloses say 95% of the power. That's not a perfect method, but at least it allows us to estimate what is the size. Well, it feels a bit arbitrary, but it's already a way to turn a blurry glow into some measurable quantity. At some point, the lens fabrication reached a level where the quality was no longer the bottleneck. The curves were precise, the glass quality was amazing, yet the point remained elusive. The shocking realization was this: lens wasn't failing randomly, it was failing systematically, and the fails were following certain patterns. Rays passing through the edge of a spherical lens are focusing to the different point compared to the rays passing through the center of the lens. It's so-called spherical aberration. Instead of sharp point, we are getting a region. And this was just the beginning. As optical systems improved, we identified a whole gallery of systematic distortions and hunted them down. Astigmatism, field curvature, one by one we checked them off the list. Each one is spreading the light in its own characteristic way, not randomly, but somehow predictably, and this predictability allowed us to fix it. By the 19th century, something pivotal has happened. The optical defects became not simply unlucky imperfections. They are classified. It's a system now. Thanks to the work of scientists like Philipp Ludwig von Seidel, what emerged was a rigorous mathematical framework. For the first time, lens design stopped to be a game and became a precise science. With this framework in hand, the path forward seemed inevitable. Correct edge aberration, make a glass perfect, add more elements, optimize geometry, and everything must be perfect. The size of focal point should be shrinking. For centuries this trend held. Better lenses produced sharper images and smaller spots. But as we pushed toward perfections, we hit a wall that math couldn't fix. It led to a haunting question. If every known aberration can be corrected, if every human error can be eliminated, what is the final gatekeeper? What actually limits size of the light? By late 19th century, the optical engineers had almost achieved the impossible. Lenses were corrected, aberrations were controlled. Image quality reached heights never seen before, and yet something stubborn remained. No matter how perfectly lenses were made, if we saw stars through a telescope, they never collapsed to a point. When George Biddle-Airy studied these images, he found a consistent mathematical structure. A bright central spot surrounded by faint rhythmic rings. Not even a random blur. Now we call this structure Airy pattern. I need you like... If a beam is huge, it's not a problem. We can use even a regular camera sensor. Just shine laser here and make a photo. But we are hunting for the point, and the focal spot of high-quality objective is way smaller than single micrometer, smaller than the pixel size in a professional camera. So how do we measure something which we can't even resolve? There is a classic brute force approach. We take a razor-sharp knife and a micrometric screw. As the blade slowly cuts through the beam, we record how the total power drops in respect to the position of the blade. The result is a smooth curve. If we numerically differentiate the curve, we can reconstruct the actual shape of the beam. Of course, the method is not perfect. It assumes the beam is symmetric, which is not always true. There are many advanced variations though, but it's not a point now. Important is that we finally got a number. We can say, between those two positions, we have 95% of the power. Armed with the blade and some math, we can finally understand what's going on at the focal point as we try to shrink it. So finally, what actually happens at the focal point? If it's not a point, then what? We have been focusing on the lens, but probably we have been asking the wrong question. Probably the real limitation is not what we do to the light, but what light we are working with. Think about a light bulb. It emits chaotic, incoherent radiation from a hot filament. When you try to focus light from such source, the lens does not see the light. The lens makes an image of the filament itself. And the fire is the same, extended, chaotic, thermal. The source structure survives the focusing process. Even stars, the closest to the point light source in the nature. It's just a geometric illusion because of huge distance. They are not point light sources. Their light is still messy at their origin. For a long time it seemed like focusing process was failing because the light source was not good enough. It was never simple and had some internal structure. And then everything changed. We learned how we can engineer the light itself. The laser. For the first time we had a light source which was monochromatic, coherent and spatially controlled. Among all the laser beams, one stands out. The Gaussian beam. It has no internal structure, no randomness. It has just a smooth shape which evolves in a predictable way. It feels like it should be the final answer, the perfect input. If something in the universe would be able to collapse to a single point, it should be this. But as we reach the focus, we find ourselves in the same place again. A spot, not a point. We have stripped away every excuse. The lens is perfect, the beam is Gaussian, the light is monochromatic. There are no imperfections left to blame, and yet we still do not have a perfect point. Using knife edge technique, let's eventually see what controls the minimal possible size of the spot. First, the wavelength. If we keep everything the same and change only the color of the light, the answer is immediate. The shorter the wavelength, the tighter the spot. It's directly proportional. Blue focuses better than red, and that's the second reminder after iridescence that all is somehow related to the waves. Secondary, what's about the focal length? It looks like the slow gradual convergence works better than the sharp one. It looks like easier to control. Once I thought the same and my supervisor literally laughed at me. Reality is totally not intuitive. The least sharper the angle of convergence, the smaller the spot we are getting. This is why a telescope objective with a massive focal length can never give you such a good resolution as a microscope. To get the smallest spot, you have to squeeze the light harder. Literally squeeze. But there is one more parameter left, the initial beam diameter. The intuition suggests if the beam initially is narrow, it's needle-like, it's easier to bring to a point. But physics says no. We have to compress it somehow. To get the smallest possible point, you have to squeeze the light the best. You have to fill the whole lens with the light. And these facts are impossible to explain if you think of light as rays. But once you think about light as waves, it's getting obvious. A large beam diameter and the short focal length means that the light waves are crashing to the focal point from the many different directions at once. They interfere with each other that aggressively that they cancel out almost everywhere except of tiny region. This is the diffraction limit. That's exactly the invisible flaw we felt earlier, and it's a universal property of the universe. You cannot trap the wave in the space which is smaller than its wavelength. So eventually what happens at the focal point? As the light converges, at some moment we are reaching the place where ray geometry breaks down. The wavefronts which were curving begin to flatten out. This region is called the beam waist. Within the space, the light behaves purely as a wave. The length of this sweet spot is defined by the relay length. Tighter we squeeze the waist, shorter the region becomes. Once the light passes the waist, it immediately begins to expand, and here math works vice versa. The smaller waist were, faster it expands. To be honest, at total symmetry. For the perfect lens, it works perfectly symmetric. Actually, we don't even need a lens to see this effect. We can see it at the end of the glass fiber. Light exits through a tiny beam waist and immediately starts to expand. Surely here I mean single mode glass fiber. And this effect that the parallel beam expands impacts a lot. For example, you can check out my previous video. If you point a laser pointer at the moon, you don't get such a tiny dot. You get a spot the size of a city. Even nearly perfect laser beam cannot stay parallel forever. And now I understand well, it's not a lie. This diagram is valid well enough, a part of tiny region near focal point. That's where geometrical optics breaks down, and you see wave nature of the light without any quantum mechanics. Don't forget to like the video, consider subscription, and see you in the next videos.